Let's continue with the second half of section 9.3. Here we are going to start by talking about the standard enthalpy of formation. The standard enthalpy of formation, or delta HF naught, is the enthalpy change for a reaction in which exactly 1 mole of a pure substance is formed from free elements in their most stable or natural states under standard state conditions. So the product here, it's a single product with a coefficient of 1. The reactants must be a single type of element the way that it is found in nature, for example, O2 in its gaseous form. Now the coefficients of the reactants may be fractional here. We are going to allow this because we want the product to be a single product compound with a coefficient of 1. So here's an example of the enthalpy of formation of CO2. It's 1 mole of carbon in its natural state, plus 1 mole of oxygen gas in its natural standard state, which forms 1 mole of CO2. Or if we were to write this for NO2, so again, we want our product to just be 1 mole of NO2. So the natural forms, or the elemental states of nitrogen and oxygen, are as diatomic gases. So this would be 1/2 N2 plus 1 O2 forms 1 mole of NO2. Remember, the coefficient in front of the nitrogen is 1/2, so that we can have a balanced equation but still have the coefficient of our product be a 1. Alright, so this, how to write one of these? Well, you would start with, so let's say we're writing this for C2H5OH ethanol. You put the C2H5OH liquid on the right side as our product, and then the left side needs to have the atoms in that compound in their component in their natural or in their elemental forms. So our left side needs to have carbon, it needs to have hydrogen, and it needs to have oxygen in their elemental forms, which for carbon is just C with the state of matter form S, which is graphite. For hydrogen, that's H2 as a gas, and for oxygen, that's O2 as a gas. Now we need 2 carbons, we need 6 hydrogens, and we need 1 oxygen. So this would be 2C, parentheses S. Now if you go to write these yourself, you don't need to include the graphite part, you can just put parentheses S, plus 3 O2, G, plus 1/2 O2, G forms C2H5OHL. So it's pretty simple. You just take the product you're looking for, you put it on the right side, its coefficient's got to be 1, and then on the left side, on the reactants, you just include the atoms that compound is made of in their elemental forms. Let's look at how we can manipulate equations to get the standard enthalpy of formation. This problem states that ozone O3 forms from oxygen O2 by an endothermic process. Determine the standard enthalpy of formation, delta HF naught, of ozone from the following information. Now this tells us 3O2 forms 2O3, where delta H equals 286 kilojoules. So we're looking for the standard enthalpy of formation of ozone. So we've got ozone in its standard state, or this is under standard state conditions, but it's got a coefficient of 2, so we need to divide this entire reaction by 2. So we divide the equation by 2. So we get 3/2 O2 forms 1 O3, and then whatever we do to the equation, whatever we do to the coefficients, we also need to do to the delta H value. So this makes delta H 143 kilojoules, and so that is the answer to this question. The standard enthalpy of formation of ozone is 143 kilojoules. Okay, so there are multiple different ways to find the delta H for any reaction. The first is experimental calorimetry. That's what we looked at in section 9.2. There are 3 calculational ways. First, using the delta HF values that we were just talking about, and I'm going to show you how to do that in just a minute here. The second is Hess's law, which we're going to cover at the end of this section. And the third is using bond energies, which we will cover in the next section. So let's look at how we calculate the enthalpy value for any reaction using enthalpy of formation values. So the general form of this equation is delta H reaction equals delta H of the products minus delta H of the reactants. So it's the sum of the heat of formations of the products minus the sum of the heat of formation of the reactants. So it's products minus reactants. So for example, for the equation, A plus B forms C and D, where these letters in front here represents the coefficients. This would be the coefficient of C times the delta H heat of formation of C plus the coefficient of D times its formation value, and then these are added together, and then you subtract the sum of the product, or the reactants, excuse me. So products minus reactants. Now when you go to do these questions, you'll be typically given a table that has the information that you need. If you don't see one of the things mentioned there. It's probably because it's an element. So the standard heat of formation for elements in their standard form is 0. So let me show you an example. What is the standard enthalpy change for the reaction 3NO2 plus H2O forms 2HNO3 and NO? So we are trying to find the enthalpy change for this reaction, and we are given this information about the 4 compounds. Alright, so let's start. We're going to do products minus reactants. So we're going to do HNO3 plus NO minus NO2 plus H2O. So HNO3, it has a coefficient of 2. So we would do 2 times negative 207.4, its delta HF value, plus 1 times 90.2, since that is NO's delta HF value. And then we're going to subtract that from the sum of their reactants. So we're going to do 3 times the delta HF value of NO2, plus 1 times the delta HF value for water. And now you just do some basic algebra here, and you get negative 138.4 kilojoules. So this reaction has a delta H of negative 138.4 kilojoules. So using these heat of formation values, you can calculate the theoretical enthalpy change for any reaction given. Alright, let's have you try one. Using the provided delta HF values, calculate the delta H reaction for the following reaction. And you should notice O2 is not listed here. Remember, O2, this is in its elemental state, so its delta HF value is 0. So pause the video and give this question a try. Okay, the correct answer here is C, negative 3,267.5 kilojoules. So you would do products minus reactants. So this would be 6 times negative 393.509 plus 3 times negative 285.83 minus 1 times 49.0. And then O2 has the delta HF value of 0. So you get C. Alright, the second way to calculate these delta H values theoretically is to use Hess's law. So Hess's law states that if a process can be written as the sum of several stepwise processes, the enthalpy change of the total process equals the sum of the enthalpy change of the various steps. Hess's law allows us to calculate enthalpy change or enthalpy change values for a reaction when we can't or don't want to measure it experimentally. Okay, so let's look at an example. The formation of CO2 can be written like this. C plus O2 forms CO2, and delta H equals negative 394 kilojoules. However, we could think of this total process as a two-step process. First, we form CO, so C plus 1/2 O2 forms CO, and the delta H of that reaction is negative 111 kilojoules. Then we take that carbon monoxide, and we add one more O to it. CO plus 1/2 O2 forms CO2. The delta H of this reaction is negative 283 kilojoules. Now you should notice that if we add these two reactions together, we would get this reaction. We've got a C on the left side, we've got a total of 1 O2 on the left side, the CO's cancel out, and then we've got 1 CO2 on the right side. Then you can also notice that if we sum these two delta H values, we get this delta H value. So that's all Hess's law is. It's taking a reaction and breaking it into multiple steps, and when you add the reactions together, the sum of their delta H values equals the delta H for the total reaction. Alright, this is because enthalpy is a state function. So here are my reactants, here are my products. So if I go from the reactants to the products in one step, it's an energy difference of about negative 394 kilojoules. I could also break it into two steps. I could go first here, then to here. From here to here is negative 111 kilojoules. From here to here is about negative 283. See how the starting point and the end point are the same, we just took a different path to get there. But because enthalpy is a state function, we can use Hess's law in this way. Alright, a couple examples I want to talk about. First, I want to establish a few rules. Now, if the coefficients of the chemical equation are multiplied by some factor, the enthalpy change must also be multiplied by that same factor. because again, as a reminder, delta H is an extensive property. So if I take this equation and I multiply all the coefficients by 2, so I get 1N2 plus 2O2 forms 2NO2, I also need to multiply delta H by 2. If we reverse an equation, the sign on delta H must be reversed. So if I took this equation and flipped it, and made it HCl forms H2 and Cl2, then I need to flip the sign, and it goes from negative 184.6 kilojoules to positive 184.6 kilojoules. A few tips about more complicated Hess's law problems. First, again, you will be given an overall equation as well as some equations that can be manipulated to add up to that overall target equation. As you manipulate the equations that you're given, you need to check for two things. First, is the desired compound on the correct side of the equation? If not, reverse the equation and change the sign on delta H. Second, does the desired compound have the correct coefficient? If not, you need to multiply or divide the equation by some number and do the same to delta H. So let's look at a complicated example. This problem states, chlorine monofluoride can react with fluorine to form chlorine trifluoride. So this is our target equation. It states, use the reactions here to determine delta H for the overall reaction. So we need to use these three equations, rearrange them in some way, and then add them together so the intermediates cancel out and we get this equation. Then we can add the delta H values together to find the delta H for this reaction. Alright, so overall we want this. So the first thing I'm going to look at is reaction 2. Now reaction 2 has ClF on the correct side of the equation, but it has the wrong coefficient. So this is reaction 2. So it's got ClF on the correct side, but it's got the wrong coefficient. So I'm going to take reaction 2, and I'm going to divide the coefficients by 2, which then also means I need to divide delta H by 2 to get 1 mole of ClF on the left side. So ClF plus 1/2 O2 forms 1/2 Cl2O, and 1/2 OF2. Delta H equals positive 102.8 kilojoules. Next, I'm going to look at reaction 1. So here's reaction 1. Reaction 1 has F2 on the wrong side of the equation, and it also has the wrong coefficient. So in our target overall reaction here, we want 1 mole of F2 on the left side, whereas the reaction 1 has 2 moles of F2 on the right side. So I'm going to reverse the equation and change the sign. So now I'm just flipping the equation here and changing the sign. Then I'm going to divide the coefficients by 2, which means I also need to divide delta H by 2. So here is my manipulated reaction 2, and here is my new delta H value. Finally, I'm going to look to ClF3. So reaction ClF3 has, reaction 3 has ClF3 on the wrong side of the equation. So in my target equation, I want ClF3 on the right side. Reaction 3 has ClF3 on the left side. So it's on the wrong side of the equation, but it has the correct coefficient. It has a coefficient of 1. So all I need to do is take reaction 3 and I need to flip it. I need to reverse the equation and then change the sign on delta H. Now what we need to do is add the manipulated equations up and see if they make the desired equation. If they do, add up the corresponding delta H values to get the overall delta H. So here are my 3 equations, and I'm going to add them up. So what you want to look for is you want to look for intermediates that cancel. So we've got 1/2 O2 and 1/2 O2 on the left side of the equations, and I've got 1 O2 on the right side. So those 2 halves cancel with that 1 O2. Next, I look at OF2. So I've got 3 halves OF2 on the left side right here, and I've got a 1 1/2 right here, which sum to 3 halves. So the 3 halves on the left side cancels with this 3 halves on the right side. Finally, look at Cl2O. I've got 1/2 Cl2O right here, and I've got 1/2 Cl2O right here, so those 2 halves cancel out. So all that I'm left with is ClF plus F2 forms ClF3. So the manipulated equations, they do add up and make the desired equation, So now I can add up these delta H values. And I get negative 139.2 kilojoules. Alright, let's try a quick knowledge check question. Given the information in the provided table, what is delta H for this reaction? NO plus O forms NO2. So use these three equations, manipulate them in some way so when they add up, they form this desired equation, and then sum those delta H values to find the delta H for this reaction. Okay, correct answer here is D, negative 304.1 kilojoules. So here I would take equation 1 and I wouldn't change it at all since it's got NO2 and NO. They are both on the correct side and they both have the correct coefficients. Then I would look towards oxygen. So I need one oxygen on the left side. This equation has two oxygens on the right. So I would take this equation or this reaction right here and I would flip it and I would divide it by 2. And then the last thing I would do is I would take this equation right here and I would use this equation to cancel out the coefficients. So this equation right here just needs to be reversed. So the ozone cancel out and the O2 cancels out. So you take this equation and flip it. Once you do that, you sum them up. That you should get this equation and you should get a delta H of negative 304.1 kilojoules. Okay. Here are two practice problems for you to try. So number 1, use this data here. And then number 2, this is going to be Hess's law problem using this data here. So pause the video, give these two problems a try, and once you have done so, the answers are on the next slide here. Here are those answers. That concludes section 9.3. I'll see you in the next video for the final section of chapter 9, Strength of Ionic and Covalent Bonds.